Hello, and welcome to our talk on Atom Overview. This specific talk will cover the path system and the RHI. My name is Anton. I'll be joined by my colleague Sid, who will present the RHI portion of this talk. But first, I'll go through the path system. And before I reach the path system, I'll dive a bit into Atom Overview as a whole. Then I'll give a brief journey through the RPI, and I'll finish by actually addressing the path system. So Atom, like all renderers, is the interface from the parent application to the GPU. Atom is split into two pieces, the render pipeline interface and the render hardware interface, which we commonly refer to as RPI and RHI. The point of the RHI is to abstract all platform divergent rendering code. So this is anything that interfaces with the rendering APIs like DirectX 12, Vulkan, Metal, etc. This is all contained within the RHI, and this way we can leverage the RPI to only use platform-independent code and not have to worry about what backends we're using. This whole section of the slide will be covered in detail by my colleague Sid later on in the presentation. And for now, I just want to dive a bit deeper into the RPI and how it takes objects from the parent application down to the RHI. So for this, we're going to follow Paolo the Panda. He lives in the game world, and he's going to make his way down to the GPU. Paolo lives in a simple scene. There's some sun, the sun is casting shadows, and there's a main camera that's filming Paolo. In order to render this, we need to render two views. One is the main view, and one is the sun view, so that we can get shadows on Paolo. In order to render Paolo needs a mesh, and that mesh needs a material. The material has multiple shaders. For example, we have a depth shader so that we can render Paolo in the shadow view, and we have an opaque shader that will render in the forward pass and the final render. For each of these shaders, the RPI will generate a draw item, and these draw items will be combined into a draw packet. A draw packet is essentially all the data we need to send through the RPI and to the RHI that we need to render the object. So once we have these shaders, how do we actually associate them with their appropriate passes? The way we do this is we have these data-driven tags, what we call drawless tags. The depth shader will have a depth tag, the shadow pass will have a depth tag, and similarly, the opaque shader and opaque pass will also have the same tag. These tags are given to the draw item, and under the hood, the RPI uses these tags to match the draw items with the appropriate passes. So, to give a quick recap, we have Paolo the Panda. He has his draw packet. The draw packet has several draw items, one of which would be the opaque draw item. That item is associated with the pass, and then the pass will send that item down to the RHI, the render hardware interface. That will pass on to the GPU, and we will get our finally rendered Panda. So now on to the main portion of my talk, which is how do passes actually work in Atom? Well, what is a pass? A pass is mostly a collection of GPU work and can be thought of as a function. It has set inputs and set outputs. Passes describe the logic of a renderer, and modern renderers can have up to or over 100 passes. The pass system in Atom is built on three core principles. One is that we should be able to build all passes entirely in C++. The other is that we also want to be able to data drive some of this creation, so we have a JSON data-driven pass system. And the third tenet is that we can combine these two and they should work seamlessly together. So why the separation? Well, because both approaches are good at different things. JSON has no build times. This means the iteration process is very fast. This leads to easy prototyping, and it also leads to easier and more portable code that you don't have to merge or recompile. And the JSON files can be hot reloaded, meaning we can reload the entire render pipeline at runtime without having to shut down the engine. C++ on the other side allows users to implement complex logic that we couldn't predict and handle in our JSON runtime. It allows for deeper customization. For example, if you want to spawn multiple passes based on some kind of custom data that you're putting in. And it allows for deeper control, so you have more fine-grained access and can access functionality closer to the RHI that you wouldn't otherwise have with the JSON pass system. So a closer look at what a pass looks like. This is, for example, a transparent pass. It has the inputs and outputs. Sorry. These inputs and outputs are called slots. So the input to the transparent pass, we have the depth buffer, we have the lighting buffer and called light list, and at the output we have the new lighting buffer with the transparency rendered to the scene. These slots are populated by what we call attachments. Attachments are essentially the data that feed from one pass into another. We have two main types of attachments, image attachment and buffer attachments. And to illustrate how they flow from one pass to another, here's this transparent pass with the inputs kind of a bit illustrated. We have the pre-depth pass, which creates the depth. The depth feeds into the opaque pass and the light calling pass. Both of these output the lighting buffer and the light calling data. And all three of these then feed into the transparent pass. So these connections allow us to have a layer of encapsulation. For example, we have an SSAO pass. This SSAO pass is actually composed of several passes internally. An SSAO compute followed by two blurs, one horizontal, one vertical. And as a parent pass, all it needs to define is a depth buffer and SSAO output. This can then be dragged and dropped into your pipeline without having to know the internals of how the pass functions underneath. So any pass that contains other passes is called a parent pass. And this encapsulation allows us to have a hierarchy. So with multiple layers of encapsulation, you can build this kind of a tree-shaped hierarchy. At the very top of the tree is the root pass, and then you can go in deeper and deeper into layers and have this kind of very complex definition. What's really nice about this is that we can also reutilize passes. So for example, you can define your cascade pass for your shadow cascades or a downsample pass for bloom. These can be seamlessly utilized without having to rewrite your function or touch any C++ code. So back to this analogy of functions. Just like in code, functions have a definition and call sites. In the pass system, we have what we call a pass template, which defines the pass, and the call site will be a pass request, which is basically a request to instantiate the template at a given spot in the hierarchy. So what does the pass template actually look like? We'll take a brief look at the JSON example. We'll revisit this SSAO parent pass that we had. We're just going to simplify it for the illustration purposes. So our blur passes will be combined to one. So we have a linear depth as input. The SSAO compute will calculate the SSAO, and then we'll blur it and we'll output it. And we'll go over all of these connections in detail and how they're set up in JSON. So this is the beginning of the JSON. At the top, we have just your standard O3D JSON header, which is not really important for this talk. The actual definition of the pass begins here. First thing is the name of the template. So in this case, we call it SSAO parent template. This is what we'll use to refer to when we want to instantiate it later on in other passes. Next up is the pass class. This is another name. This is what you will associate with your custom C++ class. So if you go into C++, write your custom pass, you'll need to register it with the pass system with this simple name. And then you can instantiate it from anywhere, either in code or from JSON, using the simple identifier. So in this case, the class we're going to use, underlying class, is the parent pass class. And next up, we'll actually enumerate the slots that this pass has. So first, we'll define the linear depth input, which is defined here. The name is linear depth, type is input, pretty straightforward. Same thing for output. We have name is output, and the type is also output. Next up, we'll enumerate the pass requests. So these are the child passes within the parent template that we're defining. So again, we're defining the SSAO parent pass. We want to have within it the SSAO compute pass and the SSAO blur. So first we'll define the SSAO compute. Here again, the name will be called SSAO compute. And this template name is the template we're using to instantiate it. So in another file, we've defined the SSAO compute template And here we're just referencing it by name. Now we'll actually specify the connections. For in Atom, we specify path system connections from input to outputs. The reason for this is that one input can only have one connection, whereas outputs can have multiple connections. One output, for example, can feed into several inputs of other files, of other passes. Sorry. For example, linear depth input feeds into both the depth input of SSO compute and SSO blur. So in order to define this input, we'll start off by saying we want to define the depth input on SSO compute. So we're already defining the SSO compute, so we just say local slot is depth input. That's what we want to attach it to. And then the attachment ref part here is what we're actually attaching it to. So in this, first we specify which pass we're getting. So in this case, we're using the parent pass. So in this case, it would be the SSO parent. So we use the parent keyword, and then we say we attach it to linear depth. So again, linear depth on the parent pass goes into the depth SSO compute.depth input. If you looked at this at a more kind of C++ programmatic way, it would look something like this. SSO compute depth input is this dot linear depth, this being the parent that we're defining at the moment. So next up, we want to define the SSO blur, the second child. Similarly, we have the name of the pass we're creating and the template we're using. So in this case, we can have some kind of generic Gaussian blur that we're using and just reusing it here. In terms of connections, we have the depth input, so it's exactly the same kind of type situation as the SSO compute depth input. We specify the name, and then we say we're getting it from the parent linear depth. And here for the output, for the blur source, we're actually getting it from the SSO compute output. So here, again, local slot is blur source, and then we're getting it from the path, which is SSO compute, and on the SSO compute, we're getting it from the output. These are all name references. And this, again, can be thought of as SSO blur.blur source equals SSO compute.output. And finally, the connections. So these would be the connections for the paths we're actually defining, which is the parent path. We want to specify our output, and which is connected to the SSO blur.output. So again, local slot, the slot we're using is output. We're connecting it to SSO blur and the blur output on the SSO blur paths. So again, you see blur output from SSO blur is going out to the SSO parent output. Can be thought of as this output is SSO blur output. And now I'll let my colleague Sid talk about the RHI.
Hi, I'm Siddharth Motgil, senior software engineer with Amazon Web Services. I'll be discussing the Atom RHI. So in this talk, I'll be talking about what an RHI is, why do we need it, and how do we solve at least the top biggest problems. There are many problems that it solves, but I'll only be discussing the top big ones. So what is an RHI? RHI is a layer that sits under RPI and above the drivers. At this point, it contains 4 gems. The RHI gem, which contains all the common functionality for all the backends, and then it has a gem for DirectX 12, Vulkan, and Metal. And they essentially contain all the API-specific driver calls and any other functionality that's very backend specific. Why do we need RHI? So in order to understand why we need RHI, we need to understand how the GPUs work. These days, pretty much GPUs have multiple command processors. Think of command processors as like a front end to the GPU. And we give each processor a bunch of work to do, and the command processor essentially parallelizes all that work across multiple shader cores. It's usually based on the limitations based on the work. So if the work needs to read memory or write memory, you can only use a certain number of shader cores. So if you can use multiple command processors, then you can use more shader cores. And the idea is that you want to use as many cores as possible. And the cores are what's interfacing with memory. In this case, it could be like L1 cache, L2 cache, or the tile memory. And the idea is that you want to be able to use all the cores to get as much throughput as possible. So it's a very complex problem. So in our case, all the backends can abstract out the command processors as command queues. So think of command queue as a command processor. It's essentially saying, hey, here's a work for this queue, which will go to that specific command processor. Under the hood, it's all virtualized, so it's not one-to-one mapping directly. So here's an example of a rendering pipeline where you have all these passes that essentially Anton discussed, which we can execute on multiple command queues, but we need to synchronize them. So if you have scanning that needs to run before the def pass starts. So there's like that vertical red bar is a synchronization point that we need to add in our GPU commands. And the same thing with the green vertical bar between the shadow and the forward pass, forward plus pass. It's green because it's a different type of synchronization construct that I'll go over later on in the talk. So what about like hardwares and drivers? So not only do we have to manage work across multiple queues, we also have to take care of multiple APIs. You have DX12, Vulkan Metal, but you also have console API. So Switch has NVN, Sony has GNM, and many more that are coming down the pipe. And you need to also take care of different types of GPUs. So you have forward GPUs, which essentially just immediately execute on the next frame. But the tile GPUs are a little bit more complex, where they have a deferred approach, where they'll bucket up all the passes in separate tiles and buckets and then execute on them. So you need to handle all of these combination, and the higher level feature developer does not need to know anything how it works under the hood. So how do you encapsulate and solve all these problems? Just as a comparison, I actually provided we're kind of lucky in the sense that the 3 APIs that we are supporting, well, not lucky, we made that decision consciously, where DirectX 12 has all of these 3 APIs have command queues, which is an abstraction over command processors, and they all have this concept of command list or a command encoder or command buffer, where we are building all your GPU commands. So how does RHI solve these problems? So in this case, I'm only going to be discussing the top big problems. So first thing is, how do you efficiently bind all your resources at different frequencies? Back in the days when people were using OpenGL, you would bind all your resources right before the draw call, which is extremely inefficient. So you have a view that doesn't change. You don't need to bind resources for a view. You only want to bind it once a frame. Same thing for a pass. If a pass changes, you only want to bind it when the pass changes and not for every draw call within the pass. So how do you bind resources for your draw calls in a more efficient manner? How do you track explicit resource dependency? So essentially, you don't want one pass to start before the other passes finishes. You also want to make sure that the resources are compressed before they are actually needed, or decompressed accordingly. So you need to actually tell the GPU when to do what, essentially, like when to execute. And then transient memory aliasing, which is essentially, transient memory is a memory that only is active for the current frame. So you can actually use memory that's written on by something earlier in the frame. So it's essentially a way to conserve GPU memory. It's critical in order to be at least conserve memory on the GPU. And then you want to encode all the GPU commands in parallel. You can't do it serially, which has been the case back in the days. Even Lumberyard they only had one extra thread, but at least that one thread was heavily used, and that can cause problems on the CPU timeline. So how do we solve these problems? We create a frame graph. Frame graph is essentially a DirectX acyclic graph of all the render passes and the resources that are used in the frame. I'll kind of go over what that really means. So here's an example of a frame graph. So this is a simple frame graph that essentially starts with def pass, then it's your skybox pass, your diffuse passes, your specular passes, merging, anti-aliasing. So as you can see, the graph can get pretty complex here. It is acyclic in nature, so there won't be any circular loops. But you need to essentially, this is all the work that we need to run on the GPU for the current frame. How do we do it in the most efficient manner and in a manner that's correct? Basically, don't have any rendering artifacts. So don't start one pass before the other one finishes. All the resource transitions happen at the correct time within the frame. So how do we do all that? So RHI does this by splitting all its work across 3 phases. So this is an easier way to understand how RHI works. The first phase is where it actually creates the frame graph. So RPI will register all the passes, and then the frame graph will essentially create a graph out of it. Second phase is serial in nature, and it's actually really fast. Second pass is where we compile the whole graph, which is compile all the views, compile all the memory, all the various parts of the data that needs to be sent to the GPU. And then the third phase is where we actually encode all the GPU commands. And this is, the phase 2 is partially parallelized, but phase 3 is completely parallelized, because that's where majority of your time would go if you have a very large and complex scene. So essentially what the RPI does, it registers all its passes with RHI, and in the RHI land, we call them scopes. There's a difference why the terminology changes, because passes are more complex. They have there's parent passes, you can redefine passes. When they get registered in the RHI land, they are called scopes. Simple. All the scopes are the same. They are essentially, think of them as a unit of GPU work that needs to be done. We essentially create a frame graph. So all the nodes of this graph becomes the scopes, and all the edges becomes the attachments that are associated with it. And then we essentially topologically sort the whole graph, frame graph. So here's an example. You have a scope that writes to a render target, and then you have another scope that reads from the same render target. And then you essentially create an edge between scope 1 and scope 2. So that tells the RHI that, hey, you need to, when you encode your GPU commands, you need to make sure that scope 2 needs to begin after scope 1, and it doesn't, and not only does it need to begin after scope 1, it needs to wait until scope 1 fully finishes. And all the render target is in the correct state to be read. Then you have your compilation stage. These are all the compilation steps that happen for the frame graph. So you compile all the work across all the queues, the transient memory, the resource views, shader resource groups, which I'll go over, and all the ray tracing shader tables. And then we actually call execute. And execute is essentially encoding all the GPU commands. So this is a really quick overview. So I'm kind of going over really quickly. So we separate all the work into different groups. And then within a group, you can have different context. So your groups can run in parallel. So every group can get a thread, or even every context can get a thread. So the idea is that you want to use it as efficiently as possible. So you can go wide on the groups or not wide on the groups, and the same thing on the context. And I'll go over exactly how they relate at the bottom, at the end. So okay, so how do we efficiently bind all the resources at different frequencies? So to talk about that, I have to kind of go over what the shader pipeline looks like. It's kind of complex. Shader pipeline can take its own talk, so I'll just kind of give you a quick overview. So we have a shader asset builder. We have our own language. It's called AZSL. It's essentially HLSL with some metadata on it. And we have our own compiler called AZSLC. It converts all the AZSL files into HLSL files. All the HLSL files go through DXC. It's an open source compiler that Microsoft released. For DirectX 12, it emits DXIL. For Vulkan, it emits SPIR-V. For Metal, it emits SPIR-V, which then we go through another open source compiler called SPIR-V Cross. That spits out Metal SL, and then we do some more processing to it, and we spit out the Metal bytecode. At the same time, the shader asset builder also spits out the SRG layout. Shader resource group, I'll go over what they are, but that information needs to be fed to the runtime for processing at a later stage. So that's how the shader pipeline works across all the backends at this point. So shader resource group is essentially, this is an example of shader resource group. These are all the variables that your shader function kernel will use. So you define your loose data in a shader resource group. So they're called SRG constants. Then your texture, any textures that you want to use, any buffers you want to use, static sampler, dynamic sampler. So that's how you would declare your SRG data in an AZSL shader. And then you can use it in the shader as is. So you basically go example SRG dot m underscore matrix, and then you can use that. But this layout and this information gets fed to the runtime. And then at runtime, your C++ code, when it builds that data and it sends it to the GPU, it knows how to bind it correctly. I'll kind of go over that. So here's a DX12 binding model. So on the left side is the atom abstraction. So you have your SRGs and then the SRG layout. And then each SRG, like SRG1, can contain SRG constants, shader resource views, constant buffer views, unordered access views, dynamic samplers, static samplers, unbounded buffer views, or image views. So that's on the Atom side. And on the DX12 side, every backend has its own API terminology and how it handles based on the drivers. So in DX12, they have this concept of root descriptor tables. So we essentially create multiple descriptor tables. I color-coded it so that you can use that to understand And so the yellow is SRG constants. They've essentially become root constant buffer views. The shader resource views become its own descriptor table. Dynamic samplers get their own descriptor table. Unbounded buffer views and image views get their own descriptor table. And there, think of them as like pointers. So the GPU knows that this is how I access this pointer in the GPU memory. So essentially, we pass this information to the GPU, so the GPU knows how to access this data. Same thing with Vulkan. Vulkan has descriptor set layouts. So essentially, an SRG becomes a descriptor set, and a descriptor set contains all the information. And Metal has this thing called argument tables and argument buffers. Exact same concept. All the SRGs get turned into argument buffers, and then argument buffers can have a Metal buffer texture. Metal is kind of different. It essentially just have this concept of buffer, and a buffer can be a buffer view. Same thing with the texture. So it has, and all the root constants actually are part of the argument buffer. So it's a little bit slower. So how do we resource bind? So essentially all the SRGs are, the RPI creates them and updates them. So essentially so it will say, hey, I need a texture, albedo texture or material texture. So it will create them. It will update them as needed, so all the SRG constants. And then RHI in the compile phase will take that information and copy it on the GPU memory. So then for that frame, it will update it, and then it will encode all the draw calls. So what ends up happening is that for that frame, all the pointers will be accurate. And all these shader resource groups are triple buffered, so you don't have to worry about CPU stomping, CPU stomping over memory that GPU hasn't consumed yet. So we track the frequency for all the shader resource groups. So pass SRGs are at a different frequency than object, then draw, then view. So the idea is that the view SRG you only bind once for your view. The material SRGs you only bind once for your material. Then you render all your objects for that material. And the same thing for your, so the worst ones are the ones that you need to bind every time. So let's say an object SRG is the worst one. So you need to make sure that that's as small as possible, because you're essentially binding object SRG right before the object draw call. So that's how we sort of solve the problem of efficiently binding resources at different frequencies. So now I'm going to go over how to track explicit resource dependency. And this is essentially how do we create fences and barriers to make sure your passes run at the correct time and execute at the correct time and finish at the correct time. So what we do is, so if you remember this example from the beginning, you have all of these passes and you have these vertical bars. We need to embed these vertical bars as GPU commands into your command list. So how do we do that? We actually have compiled buffer barriers, image barriers, and async queue fences. So what we do is we have these functions for each backend where we track all the buffers, images, and resources across all the queues. So thankfully, the backends that we have actually have kind of support for that. So DX12 has fences and resource barriers. Vulkan has Vulkan fences, memory barriers, and semaphores. And Metal has this thing called MTL shared event and use resource, which allows us to transition resources. So how do we track explicit resources? So imagine if you have a scope that writes to a render target. It has its usage is a render target and you're writing to it. Another scope that reads from the render target. Then that scope 2 writes to a UAV, which is just a buffer. And then you have a scope 3 and scope 4, which are on a different queue, and they are reading from this resource. So how do we encode all the GPU commands such that this pipeline works correctly? So what we do is in the prepare phase, we basically, this is where we're building the frame graph. We actually track the lifetime of all the resources. So we know that resource 1 started in scope 1 and it ended in scope 2. And then resource 2 started in scope 2 and it ended in scope 4. And we know all the details related to it. And in the compile phase, we cache all the transition. So for DX12, we have this thing called transition barriers. For Vulkan, they're called memory barriers. And on Metal, there's this thing called fences that you can use. So for in the compile stage for DX12, so I'm only talking about DX12 because that's like most famous and what people are more comfortable with. In this case, we want to transition the resource 1 from common state to a write state, then from a write state to a read state, and then resource 2 again from common state to a write state, and then from a write state to a read state. So these GPU transitions need to happen at the right time, and that essentially tells the GPU to run everything perfectly in parallel. So what we do is we cache the prologue and epilogue transition. So prologue is it needs to run before the scope, and epilogue is it needs to run after the scope. So in the execution, so we cache the information in the compile phase. In the execution phase, we actually embed the actual GPU command. So you see all the gray bars? The gray bars is where we're embedding the GPU command to change the state. So right before we call scope 1 build command list, we essentially we do all the barrier changes for all the resources. So in this case, it will be resource 1, switch it from common state to render target state. And then for when we're embedding the GPU commands for scope 2, we do transition states for resource 1 and resource 2, and then change it again for resource 2 after scope 2. So that's essentially how we switch all the transition barriers, and we make sure that scope 3 does not start before scope 2. Because once we do these transition barriers, it means that once the scope 2 ends, all the caches are flushed. So when scope 3 goes and tries to read the memory, it's there, like the information is there and it's correct. If you don't have these barriers, then it may read memory that scope 2 hasn't quite finished yet, or it hasn't compressed yet or decompressed yet, so it may read bad data. And then you have a whole bunch of pain on your hand and artifacts that are really, really hard to track down. Well, these are resources. Well, what about sub-resources? Because really, textures have MIPS, arrays, then you have your aspect slices, because you can have a color, depth, or stencil. We actually need to track all the sub-resources, and it can become a really complex problem. So we kind of solve it by using this thing called interval map, where we flatten out all the sub-resources to an index, and then we essentially use an interval map to track resource state for a contiguous set of sub-resources. So that way, we only need to track the contiguous set. So like from 0 to 23, if all the MIPS, arrays, and aspects stay the same, then we only track the state from 0 to 23. Only when, let's say, aspect 1 changes, will be split into 2 separate objects, and then we can track it for 2 separate objects. So that way, it's way more efficient and fast. And then we need to talk about what about they're in different queues? So the actual synchronization construct changes. If it's a different queue, it's not a transition barrier, it's actually a fence. So you need to check, hey, scope 3 that's reading from scope 2 is on a different queue. And if it is on a different queue, not only do you have to do a transition barrier, but you also have to apply a fence because it's on a different queue. So it's a different command processor under the hood. So DirectX 12 provides fence, Vulkan is called a semaphore, and Metal is called a shared event. So all of that's happening under the hood. So it's all really hard to cover in details, but that's essentially what's going on at a higher level. But under the hood is like tracking like multiple different changes across all the sub-resources, across different queues and barriers. So now how do we do memory aliasing for transient resources? So this is essentially reusing the same memory that was used earlier in the frame, again, further down the frame, when you know that memory is not going to be needed anymore. So how do we do that? Here's an example of transient memory. So you have scope 1 that writes to a render target 1, scope 2 that reads from it, and then writes to render target 2, and scope 3 reads from render target 2 and writes to render target 3. So if this was your rendering pipeline for the frame, render target 1 and render target 3 can alias. They can literally use the same memory. So whatever one, as long as scope 3 begins after scope 2, you can be sure that it can use the same memory as render target 1, because nobody needs render target 1 anymore. Scope 2 has already read it. Nobody else needs it, so that memory is now essentially available for free. So just to make it clear, we're not explicitly allocating and deallocating, we're essentially sub-allocating from a heap. So it's like instant. It's just memory pointers moving back and forth. So whatever the memory pointer for the render target 1 is, we essentially just say, hey, render target 3 can use that. So we have multiple allocation strategies. We have a fixed allocation strategy where we provide the full budget of all the all the pools. We have a paging strategy where we essentially allocate pages that can grow and shrink in size. And the one that we actually use by default is called the memory hint. So we traverse the frame graph twice. We traverse it once to figure out the exact memory size that we need for all the for all our heaps, because we essentially know, hey, these are all the resources. This is how we can alias them. So we really only need exactly 600 megs. So we only want to suballocate 600 megs in that case. So that's the one that we currently use. And then how do we synchronize this memory? So the idea here is that you still want to add a synchronization mechanism between scope 3 and scope 2, because scope 2 is the one that's going to read from render target 1 and then write to render target 2. So scope 3 cannot start until scope 2 finishes, because render target 1 and 3 are using the same memory. So we essentially add a synchronization construct there. So it's a fence in this case, or actually for DX12 it's an aliasing barrier. There's an actual resource barrier that's made for alias memory. So if there's a full overlap, we add a synchronization construct. If there's a parallel overlap, we add a synchronization. And if there's actually no overlap, then we don't need to do anything. Then we don't need any fences or meshes. So in this case, for DirectX 12, we use heaps to allocate all the transient memory out of, and we use aliasing barrier. For Vulkan, it's just device memory, and then we have memory barriers. And then for Metal, there's a heap, and then there's a shared event that we use. We actually have a profiler built into our Atom. So you can turn that on, and you can kind of see, it's hard to explain it over there, but at the top line are all the scopes, and vertically is essentially all the memory that's used. So all the aliased memory are horizontal. So you know the depth stencil, you don't need the depth stencil after the depth is resolved. So that whole chunk at the top becomes free. That can be used by all the post-processing or anything else that comes down the line. So that you know, horizontally it's all aliased. Vertically it's not aliased. So now how do you encode all the GPU commands in parallel? So I'll give you a quick example. So imagine if you have 5 scopes. So you have scope 1 that has a cost. The cost in this case is also arbitrary, but let's say it takes 2 amounts of work, and scope 2, 3, and 4 takes 1 amount of work, and scope 5 will require 100 amounts of work, because scope 5 has, let's say, 100 meshes. You can't blindly just allocate a thread to each scope, because that can be inefficient, because now you're going too wide. You don't want to go too wide, and you don't want to go too vertical. So the idea is that you want to figure out the perfect balance and drive that balance based on your scene. So in this case, you essentially want one thread to do multiple scopes if possible, and then multiple threads to do one scope if needed. So in this case, imagine if you have one thread can take one command list, and one command list can do 10 amounts of work. So if that's our scenario, if that's our configuration, we can say, hey, create one group. The one group gets scope 1, 2, 3, and 4. I know you can do 10 amounts of work, but that's where we cross the line because it doesn't fit. And then scope 5 the whole scope 5 goes to group 2, and then within group 2, scope 5 has a lot of work, so scope 5 can also go wide. So instead of doing one thread doing all hundreds amount of work, we have thread 2 to 11, essentially 10 threads doing 10 amounts of work. And this is sort of the perfect configuration that you would want to achieve. So you want to go parallel on groups, and you can go parallel on the context. And it's all based off of, if you are able to do it, you would do it. And you can even make them go serial if you want. It's kind of completely up to you how you drive that information forward. So you still want to maintain order. And by that I mean group 1 needs to still go before group 2, needs to go before group 3, and then within the group, context 1 needs to go before context 2, before context 3. And the idea there is that there's a reason why that's the case, because you have, the way we split the groups, they have dependencies. So you can have, the dependency could be like a swap chain, or it has a fence boundary. So let's say your group 3 and group 5, let's say group 3 and group 4 had a fence between them. That means group 4 cannot start until group 3 finishes, in which case we would have to create a second group just for scope 4. So we need to still take into consideration fence boundaries, but based on that, we have criteria right now that how we break groups. So depending on the cost threshold, so if it goes over the 10 amounts of work, the swap chain check, depending on if it's a different queue or depending on if it's a fence boundary, we create multiple groups. And then within a group, we'll create multiple contexts based on the amount of work that it needs to do. So we maintain group ordering and we maintain context ordering. It's very important because if you have like a transparent pass, which has many meshes that need to render from back to front, we want to make sure that the context for all the meshes from the back needs to execute first, and then the context 2, and then the context 3, and then the context 4. So for DirectX 12, they actually provide ability, actually all the APIs, in this case explicit APIs, provide the ability to maintain group order as well as context order. So for DirectX 12, you can execute command lists as long as you execute the group 1's command list before group 2, which is what we do, even though it's parallel, but we always make sure that group 1 will call execute first. Like even though if group 2's thread finishes first, it will just wait until group 1 finishes and calls execute, and then group 2, and then 3, and then 4. And then within a group, you have context. And these contexts also maintain order. So context 1 will, in the command list block for DirectX 12, the context 1 is first in line and then context 2. And same thing for like Metal, we create the parallel encoders. The encoders maintain order. So 1 gets executed first and then 2 and then 3. And then that's how we maintain order across a whole pipeline. So this is a lot of information for RHI, and it's actually pretty huge. It has a lot of code in there. So there's a lot of stuff that I actually did not cover, specifically because of time constraints. But specifically, I didn't cover like anything related to ray tracing abstractions, indirect draw abstractions, streaming images, query, subpass. Subpass is basically how do you use tile GPUs, command list, even specific API details related to DX12 versus Vulkan versus Metal. So the RHI is huge. I've tried to cover just the top 4 problems. And if you have any questions, I actually want to give thanks to the RHI team because it's a humongous effort across a lot of engineers. This is the link that actually has links to all the websites, so the Discord, the docs site and everything else. And this is the Discord graphics channel. Feel free to ping the graphics channel. Most of the Atom rendering guys are in there, and then they will be able to answer any of those questions.